Now, what we were saying before is that the amount of PMA will be changing the point at which the system operates, and therefore, by measuring that, by changing the operation point through IPTG in the transcriptional network or PMA in the cascade, in the phosphorylated cascade, I will be changing sigma 1, 2, as shown here. As we change PMA, which is what affects the MEC-ERK cascade, we are changing basically the K, right? The value of K, and therefore sigma 1, 2. Very good. And so what this says here, then, if this is the stimulus and I have element 1, element 2, then the variance of y, of y1, which is the log of x1, flat with respect to the covariance. But the variance of the downstream element, of the log of the downstream, will be quadratic. It's a very specific variance-covariance kind of relationship that results from the Lyapunov equation. How does this work? Well, in the case of the E. coli transcription network that Van Oudenaarde did, remember that we have a gene G0 and we have the repression of 1 and 2. By changing IPTG, I can change the covariance between the log of the abundance of G1 and the G2. And so you can see here the variance of G1, and here the variance of G2. Now, of course, because it's a repression, the covariance is negative, and you can see that even though we don't have a lot of points, there is a clear tendency of these to be quadratically determined. And the same is seen for the PMA stimulated RAS cascade, in which we look only at the MEC-ERK fluorescence. And again, the MEC fluorescence hardly depends on the covariance between MEC and ERK, but the ERK fluorescence clearly depends quadratically on the covariance between MEC and ERK. And so here is where you have to start to do some amount of statistics, and you can say, okay, which is the more parsimonious model, or the most do model selection, right? We said that MEC to ERK is where K has to be, but you can suggest, okay, no, let's put the K, because I don't know, in ERK to MEC. And then you see what is the best fit, right? Which model gives you the best fit, so that you select one of the two models. And here you have this, the test. If you assume MEC phosphorylates ERK, you have this, but if you assume that ERK phosphorylates MEC, you have this very lousy model in which a straight line should represent this and a parabola should represent this. And when you do the, any kind of statistical test that you want to see how well one fits the other, clearly this will be the better one. I assumed only a adjacency matrix that is a two protein or gene system, right? But suppose that you have something more complex, for example, two things having affecting X2, X1, X3 affecting X2, not just X1 to X2, or a cascade that is a little bit longer than just X1, X2. So in that case, things get a little bit more complicated, and the variance versus covariance story changes, and it's a little bit more, you start to create loops. For the same covariance, you may have two states and two different variants. So the plot thickens there. But basically here I wanted to show one way in which we can go from more or less first principles, which is the linearization around a stationary state, and use the Lyapunov equation in order to see whether there is any a way of inferring the adjacency matrix from the covariance matrix. So that's what we just did. Very good. So,
sorry, this is one question. So you were able to convince us, and I'm convinced because it's a technique that
solved.
So that was, no, but I mean, we have been working on this inverse covariance matrix in other contexts, and we know the story. Moreover, I mean, all the topologies that you have been showing us are three topologies for which it is a theorem that the inverse reproduce the topology. Well, it is a theorem.
In the causal inference world, right? Yes.
Yeah, exactly. Why don't you use it right in this way? Just compute the inverse covariance matrix and then sort edges according to this. Because I mean, I don't understand why this complicated fitting procedure and just not using the.
It's not complicated. It's very simple. It's trivial.
No, it's trivial for 3 spin.
No, but the reason why I'm doing it like this is because I want to start from the dynamic equations and see from the dynamic equations, right, from the physics of it, if you will, in a linearized case, what is it that I can do, and because. You know, in the stationaries, in the equilibrium state, we know how to deal with it, right? Because the matrix is symmetric for, you know, action and reaction, says A to B, you know, somehow is related to B to A. In that case, we know how to do it, and it comes from, you know, a Boltzmann distribution. But in the general case in which you have non-equilibrium, so in which A is a little bit more complicated, then this is the way to solve it. And I wanted to see the limitations of this, right? So I wanted to learn from this, not from the statistics or of the causal inference and, you know, the surgical. Well, because in the Pearl concept of where the theorems kind of come from, is the concept of surgical interventions, right? And you have to intervene. Here, I don't intervene, right? The only interventions is put PMA or IPDG, but the noise of the system is what is doing the perturbations. And I wanted the natural fluctuations to make the surgical.
Thank you.
Yes.
So you understand correctly that basically you are also assuming that there is no time delay between events.
Ah, very good. Yeah, exactly. Because, thank you. Yeah, finish your question though.
No,
that's the question. Yes. Now that's very important because usually you say causality. Thank you, because I forgot to mention this. Causality. Yeah, I don't say this, but causality would say you have a temporal component. Something has to happen first in order for the effect to, and so there has to be. There have been ways in which you look at a lagged system in which you measure at time t and at time t plus delta. And so whatever happens at times t affects downstream, if you have the right time scales, at t plus delta. Here, we have the same time, which is another interesting concept, right? Here, what we are assuming is the stationarity of the system made you forget somehow the causal, you know, but what is included here is somehow that the stationarity of the system is also contains this causality through A linked to the covariance matrix, non-time lagged covariance. So there is no lag here, and this is an interesting thing. I wanted to understand whether we can, because it's very difficult to do time lagged experiments, right? And you cannot resolve all the time scales. So in this case, I'm trying to understand what is the limitations of doing it at one time, in which the experiments are a little bit clearer. Yes?
Is that the same reasoning why you're not modeling negative feedback loops? Because you're looking at the fluctuations in noise and not the real.
The negative feedback loops would create the network would also stabilize in some way, and so, you know, A will, you know, even if it is a long one, A will, the noise from A will go to B, from B to C to A, and eventually the noises have to stabilize in a way, and the adjacency matrix will contain that feedback loop structure. But as we said here, that the variance versus covariance becomes a little bit more complicated. Even in this simple case, if you have feedback loops, you will have all kinds of weird ways in which the covariance, the variances of each of the elements depends on the variance. So it becomes a little bit more untreatable. And we did that, but you know, it's a little bit. So in this case, this theory is very simple. It just works well when you have a topology and you don't know and you know that A interacts with B, but you don't know whether the causal direction goes from A to B or from B to A. So that's what we are trying to do. And so I think that I'm out of time. We will have more time. Okay, so.